Matthias Becker and Emanuele Copello, Jonas Lang, and Yong Su, who are all members in my group, and I'm very happy to present this work today. So what is the motivation? Okay, no. So, or what is the goal? So what I want to show you today is especially here to connect to this plot. So this is, so to say, the money plot that I will show you in the end and explain you. And the goal is really to connect dark matter with inflationary physics and really see how, for instance, freeze-in dark matter can be connected, or one can get basically, or one has to be careful how to interpret parameter space, as we will see, based on the inflationary model behind, for instance. I also want to stress that, in my opinion, the combination of cosmological surveys like Planck or CMB stage 4 with laboratory experiments like the LHC is very interesting. And also then to link the early universe with the present day constraints. And basically the main question I want to answer today is, how can physics of inflationary heating impact our interpretation of experimental results in the context of the dark matter freeze-in scenarios? So, but let's start first. Why dark matter and what is dark matter? And we all know dark matter is very motivated out of different reasons, like the rotation curves. And additionally, we have the very precise value from the cosmic microwave background that allows us to match certain models to the Planck value of the Rayleigh abundance. Then, of course, still the question is, what is the dark matter? And of course, the question was for a long time, we were maybe hoping for the WIMP miracle. But thanks to the experimental efforts, and for instance, you see here the dark matter mass plot and the dark matter nucleon cross-section, that the room gets closed and narrowed down. And I would claim it's a right way to say that people get getting nervous and thinking about other possibilities beyond the WIMP, which doesn't mean that the WIMP isn't there, but one gets, of course, one thinks, why haven't we seen anything yet? And there are different possibilities. For instance, a more complex WIMP model, such that we can evade these bounds. It could also be that there are exceptions, so the famous three exceptions that are always getting added on, like early kinetic decoupling, other effects like bound states, or that we have a completely different dark matter candidate, for instance, primordial black holes, wavy dark matter, etc., etc. Or, for instance, that instead of the freeze-out picture that we have in the WIMP picture, we have, for instance, a freeze-in model. And this is exactly what I want to concentrate on today. And this is a nice summary that I found in the CERN Courier, which I find kind of nice, because here you see in the mass and the interaction strength of dark matter models where we lie. And this here is the WIMP. And for the WIMP, we are basically lying for lower dark matter masses and lower interactions. But of course, we want to hunt down the full landscape of dark matter candidates once. And in particular, I want to concentrate today on the feebly interacting massive particles, the so-called FIM. As I said before, we have, thanks to the Planck measurement, a very precise value of the Rayleigh abundance. And this allows us to theoretically predict our Rayleigh abundance. And this we can do with a well-known Boltzmann equation. So we can describe the temporal change of the dark matter density in the evolution of the universe by taking into account the expansion of the universe on the one hand, and on the other hand, the interaction with the other particles, depending on your dark matter model. If now the dark matter is in contact with a hot thermal bath with a standard model from the beginning, this is the so-called freeze-out picture that we have in the WIMP. So we have still larger coupling such that the dark matter particle from the start is in the thermal bath. And then we can solve the Boltzmann equation and see how much Rayleigh abundance would we still have today, and compare if we get the right value. So as I said, assumption for the WIMP, for the freeze out of dark matter, is we have an interaction rate with a thermal equilibrium. We can solve this equation. So as we are in an equilibrium, we first start with the equilibrium distribution here in the normalized number density of dark matter versus the temperature, the cooling down. And at some point, the expansion of the universe is larger than the interaction strength, and then you see here the typical freeze out. And then we can take the value of today and compare with the relic abundance. Now for the FIMP, we have a slightly different setup. Here, the FIMP, as the name says already, in contrast to the WIMP, has only very feebly interactions. For instance, if we have a parent particle and here the dark matter particle, here the interaction strength of this coupling, YdM, to the standard model is very small. And this is also why in the beginning, it was not in context or not in the thermal bath with the thermal plasma, but the parent particle, which then produces the dark matter particle from the decay of the parent particle. So then the whole freeze out is no freeze out anymore, but the so-called freeze in, because as I said before, the dark matter particle is not in equilibrium with the standard model bath. And this is why it gets slowly produced from the parent particle in the evolution of the time until it reaches a constant value, which we then call freeze in. And this is exactly what I want to concentrate on today, the so-called freeze in scenario. But then the question is, of course, okay, we have now the idea of freeze in for dark matter, but how does this connect to the full evolution of our universe? Because in principle, we understand very well, okay, we have the Big Bang, we assume we have something like inflation, the universe expands, we form protons, we have BBN, we generate the cosmic microwave background, and later the structures that we have today. But the question is, okay, at which time did actually, or where could the freeze-in, or where did the freeze-in potentially happen? Was it very close to the inflation in the radiation dominating epoch or the matter dominating epoch? And this is, so to say, why what is interesting is, in this case, the evolution of the energy density. So here a small recap for the evolution, or so to say, the evolution of energy densities in a nutshell. So as you all remember, we have here the Friedmann equations. And the first one, we have here the dependence on the curvature and the energy density. If this is non-zero, we have some expansion. And on the other hand, we have the second Friedmann equation that depends here on the second derivative of the scale parameter. And also, if this is non-zero, we have some accelerated expansion. And you see now, of course, already depending on the energy content we have in the early universe, here the evolution changes. And what can we distinguish? We can in principle distinguish three energy contents that we know in the early universe, namely the radiation, matter, and the cosmological constant. And here the energy densities scale differently with respect to the scale factor. So here the radiation goes with 8 to the -4. At some point, the matter domination kicks in, and later on, the cosmological constant kicks in, and also here with respect to the pressure. Why I'm interested, or why do I mention it? Because as I said, we want today look into what happens if we assume that the freeze-in does not happen like usually assumed here during radiation domination, but if we consider, so to say, an earlier reheating period out of the inflation. So why do we then need something additional if I said, okay, we understand the evolution of the universe so well? And this comes because we can describe the evolution of the universe based on the energy content of the universe. But when we do this, we realize actually that we have two problems. One of them is the so-called horizon problem, and the second one is the so-called flatness problem. So as we just talked about the energy densities, we have here the omega parameter. The omega parameter is, so to say, the energy density just normalized. And you see also here, or what we have seen before, that for radiation and matter domination, here the second derivative of the scale factor is smaller than 0. So this means that here the prefactor in generally is positive. meaning the evolution of the curvature, the energy density of the curvature will always expand. On the other hand, we know from our experimental values, for instance, from the combination of supernova data and the CMB, that the universe is pretty much flat, and we have basically almost a zero energy parameter from the curvature today. So this means if we have here some diverging behavior during the evolution of the universe, extreme fine-tuning would have been required, and the question comes, why is the universe so flat? And you see already, if here this parameter a dot dot would be positive instead of negative, we would actually converge and we would have no fine-tuning problem. The second why it's interesting to think about inflation, or why we think there is some phase of inflation, is the whole so-called horizon problem, because one can also show that, okay, we have here tiny temperature fluctuations in the CMB, but they are so tiny, on 10 to the minus 5 order with respect to the total temperature, that in principle we can only explain a causal contact up to 3.5 degrees of this full 360 degrees sphere. So the other reason why it's interesting to also think about inflation is the question to answer, why is, so to say, our world, or why is the CMB so homogeneous? So if we then want to solve inflation, we can, so to say, as I just mentioned before, we could solve the flatness problem, for instance, if the second derivative of the scale parameter is simply or negative, so to say that the full thing here is positive. And you see already by this Friedmann equation that this is, so to say, easily reachable when the pressure is simply, so to say, smaller than 1/3 of the energy density, or simply negative. And this is why, so to say, the standard solution to explain inflation is to introduce a scalar field to the standard model Lagrangian, which has a certain potential and a kinetic energy. And this you can describe then the energy of the density of the inflaton by the kinetic energy and the potential, and also the pressure. And you see already, if here the potential is much larger than this term, then we get here a relation of the pressure with respect to the energy with a factor of a minus. So actually we can solve the flatness and horizon problem, because then the pressure would be smaller than the energy density. So this also means that the potential energy is much larger than the kinetic energy. So this means why one also says a field that is slowly rolling down a potential. And as I just said, as this here is then the, so to say, positive, we generate a phase of accelerated expansion before the radiation domination that we've just seen before. So the idea is we have here a scalar potential that is rolling down until we basically, or the inflation happens as long as we are slowly rolling. And as we have seen before, we are slowly rolling as long as the kinetic energy is small, or in other words, as soon as the kinetic energy of the potential gets large, then one can say that inflation ends. And this is, so to say, measured in the so-called here slow roll parameter epsilon. So once inflation ends, we end up here at the minimum of the potential. And as we have still some speed, the potential is oscillating and then starting to decay. And here it depends now on our model, what we assume with respect to the inflaton and how it can decay in the end to generate the standard model bath. And depending, we can have here, for instance, fermionic or bosonic reheating. And so to say, we have, so to say, the energy density of the inflaton, it will decay as we are relativistic into radiation. And at some point, the energy density of the inflaton is equal with the radiation energy density. And this is what we then call the so-called reheating temperature. And this reheating temperature is, so to say, the interesting bit when we basically go from the previous picture where we only started with radiation domination by, so to say, having an inflationary phase before. So then we can put everything together, and this is what you see now here. So this is again the scale parameter, and this is the logarithm of the so-called Hubble radius, which depends here on the pressure and the energy density of the evolution in the scale parameter. And this here is, so to say, a sign or a certain physical scale. And now, besides the radiation domination, matter domination, and cosmological constant that we'd seen before, we introduce now a phase of inflation and then reheating. And you see that before here, the Hubble radius, so to say, here is, so to say, here the scale is larger, then it goes, so to say, exits the horizon, and then it basically comes in again, and we get this typical inflationary picture. So of course, now you can wonder, okay, so of course I want to connect inflation, I talk about freeze-in, but where's the connection now? And as I mentioned before, if we have freeze-in, what we usually assume is that the freeze-in mechanism happens during radiation domination. So this is the usual assumption, the usual freeze-in picture, where the reheating temperature, so the temperature when the energy density of the inflaton in the radiation is the same, is larger than the scale of the parent particle mass. So the mass of this parent particle that decays then into the standard model and the dark matter particle, and generates, due to the freeze-in mechanism, the dark matter content that we observe today. The question is now, what happens actually if we have another setup, if the parent particle has a mass that is larger than the reheating temperature, and meaning we have the freeze-in production during the reheating phase? And also, how does this then change the interpretation, for instance, of experimental exclusion plots? And this is what I want to discuss today. So let's first, so the goal is now to look to dark matter freeze-in production during reheating. But before we jump to the reheating, let's recall the freeze-in, how the expression looks like in the usual assumption when we have the freeze-in production during the radiation phase. In order to do this, I want to introduce to you our model setup, because at some point, of course, I have to specify what is the parent particle and what is the dark matter particle, and what is the standard model particle. And so in principle, what we have one parent particle P, which carries the standard model gauge charges. And then we basically have the dark matter, which is charged under a Z2 symmetry, that is stable. And then we can have basically two different spin assignments. So either that the dark matter is spin half. So this is, so to say, the Majorana dark matter model, where the particle has spin 0, or the other way around, which is a scalar singlet dark matter model. So in principle, it depends on these two assignments. So what I did now here, so to say, gray shows you the interactions that I have in the Majorana dark matter model, blue, the one in the scalar singlet dark matter model. And when you have both, you get both at the same time. So in principle, what I look at now is, so to say, here, a parent particle X, which generates a Majorana dark matter particle, and here the corresponding standard model particle. Or I start here with a vector-like fermion, generating a standard model particle and a scalar singlet S dark matter. What is then relevant for reheating? Because remember, we want to study how is, so to say, the freeze-in production changed if I also include the reheating effects. In this model, I have here the bosonic reheating, and here in this model, I have the vector-like fermion. So I have some fermionic reheating. So this here is the coupling of the inflaton with respect to the parent particle. What I neglect now is the non-thermal production of dark matter via the inflaton. So for instance, you could directly look how does, so to say, the inflaton decay into the dark matter particle, here the Majorana or the scalar singlet. This I neglect because otherwise we would not even end up in the freeze-in scenario, because then we would have more, so to say, it would directly be produced. And we also neglect the Higgs interactions. So for instance, here this parent particle could have an interaction with the Higgs or the inflaton, or here similarly, So in upcoming work, we will also basically want to do a big map when we go from one regime to the other and study the different effects. But for now, I basically reduce myself to these interactions of the decay and the reheating. So this is the setup to keep in mind when I look, so to say, in these two types of models, the Majorana dark matter or the scalar singlet, having either bosonic or fermionic, featuring bosonic or fermionic reheating. So as I promised before, first the recollection of the usual freeze-in production. So here the freeze-in happens during the radiation domination. So the standard case, the reheating temperature is larger than the temperature where the freeze-in happens. And then I can write down the Boltzmann equation. I depend here on the decay rate of the parent particle, the mass of the parent particle, here the temperature, and here the Bessel function. And roughly spoken, here is the yield, it's the gamma, the rate over the Hubble parameter. And as I said, depends here the parent particle, the rate, and goes with t to the -3. This is the standard case. But as I said, now we want to look at how does this change now when we go here from producing it in the radiation domination, but here during the reheating phase. So now, per definition, the parent particle mass is larger than the reheating temperature. One bracket here, of course, what one needs to consider is also how quickly thermalizes the parent particle with the standard model bath. If you think about usual freeze-in scenarios, what people usually assume that the parent particle thermalizes very quickly with the thermal bath because it actually has larger couplings and is not feebly interacting with a standard model bath. And of course, we needed to make sure that if we study all the reheating procedure, or in other words, the freeze-in production during the reheating, that this condition is fulfilled. So we did an estimate, and in principle, what we found, in order to require fast thermalization of the parent particle, so that we can assume that it's in equilibrium with the standard model bath, the condition is here that the ratio of the parent particle with respect to the reheating temperature should be of a moderate scale. So basically, as long as this ratio is not too huge, this assumption is a good assumption that I do. So this is just in the following, in case people wonder. So here we assume the parent particle is quickly thermalized based under the assumption that we cannot have too large hierarchies of the parent particle and the reheating temperature. Okay, keeping this in mind, that this is a good assumption, we want to study now how the freeze-in happens if we are in the reheating phase. For this, we start with a generic potential of at the end of inflation. So here, this is the inflaton to the K. So the K is a free parameter with a certain mass scale and a coupling lambda. What we then can do, as we have seen, we can describe the energy density of the inflaton in terms of the potential. We can also describe the pressure in terms of the potential. And the equation of state parameter is nothing than the energy density parameter over the pressure. And here in the average brackets, because we are at the end of the inflation where it oscillates and we average over the oscillations. Together with the Friedmann equation, what we then can do is we can write down the coupled equations of the energy density of the inflaton and the radiation. And of course, it's connected via the decay of the inflaton, because the inflaton decays into the radiation or into the fermionic or bosons. And of course, the more it decays, the more we get energy density of radiation and the less we get from the inflaton. And both are connected here via the Hubble parameter, which is here connected by the energy density of the inflaton and the radiation. And again, the reheating temperature is defined when both energy densities are equal. Okay, so this means we have now at hand how we can describe the evolution of the energy densities that will later influence the freeze-in production. What we did of course calculate or numerically analyze all these equations. Just to give you an idea, I do now an approximation, but this is not the approximation that we actually did in our study. Because what we can now assume, we see we have here the coupled equations, and now just for intuition, I look now into the energy density of the radiation to get a little bit of a feeling how the full system evolves. So here I simply assume that this rate is small with respect to Hubble, and then I can basically get here this expression here. So here I have the energy density, and then it depends, as I said before, how much inflaton in quotation marks do I have, and the rate, and here the evolution of the scale parameter. Because what is now interesting is that depending on the potential, and depending if I have a fermionic or bosonic reheating, the evolution of the inflaton energy density and the radiation density changes. And this we see here. So as I said, I have here the possibility of bosonic reheating. Then, for instance, this goes with the inverse inflaton mass. I have the possibility of the fermionic reheating, where I'm linear with the inflaton mass. If I have these rates, I can calculate the evolution, or I can calculate the energy density of the radiation. And as I said before, we depend now on the inflat or on the reheating potential. Remember, this was the phi to the k. So now, depending if we have bosonic reheating or fermionic reheating and different powers of the inflaton field, the scaling of the energy density of the radiation changes. For instance, you see here the energy density of radiation for bosonic reheating, k equals 2, is the same for bosonic reheating and fermionic reheating. But for k equals 4, you see we have a difference in the bosonic and fermionic reheating in the scaling of the radiation density. And the same applies then to the evolution of the temperature, or as the Hubble parameter depends also here on the energy density parameter. Of course, we also change the evolution of the Hubble parameter. So this is where the connection comes from. And how does the evolution then look like? So this you see here. So this is the scale parameter, and this is the energy density. The dashed line is the energy density of the inflaton, and the solid line, the energy density of radiation. Here for k equals 2, we just saw that this is the same for bosonic and fermionic reheating, so this is why there's only one plot, but it's different for k equals 4, bosonic and fermionic. So now what we see, what we expect, first we have more energy density of the inflaton, but at some point when the energy densities are equal, we basically have more energy density of radiation. So, and this is exactly here at the reheating temperature, where, but per definition, this density is equal. And you also see now that for k equals 4 bosonic or fermionic, here the evolution looks different. So here, for instance, it's steeper than in this case. So here in the bosonic case, here it scales with a to the minus 1, here with a to the minus 3. And on the other hand, you also see, in case you're interested more in the evolution of the temperature, you see in red the evolution of the temperature with respect to the scale factor.
Hi, Julia.
Yes.
Can I ask you something?
Sure.
Yes. Well, okay, we understand that there is a period of reheating, and ARH is the end of the reheating period, right? But when, what is the moment at which the reheating starts here in these plots?
Sorry. No, the A end is, so to say, the end of inflation. So basically where it starts is here at this point. And then, so to say, it starts, so the A end is defined with respect to inflation. So A end is, so to say, at the end of inflation. And then it starts until the moment where, so to say, this ratio is 1. So here where the energy density of the inflaton and the radiation is the same.
Yeah, this is the end of the reheating process, and then starts the radiation.
Exactly.
Yeah, but so for instance, in the middle plot, what about this discontinuity when the curves go down steep, like in the beginning? Maybe yeah, this is the point where I'm not understanding. It's about the initial condition that you are
exactly. Yeah, I think maybe okay. How should I phrase it? I mean, I show you in the end when we connect it to the inflationary models what we exactly take as initial conditions. But in principle, we basically take that at the end of inflation, we are basically having at the end, so to say, the full energy density of the inflaton, which basically sets the initial condition of the first energy density. Okay. And then basically this pumps it then into the radiation. But I show you in the end in more detail what were the initial conditions.
Thank you.
Yeah, of course. If there are any questions, feel free to jump in. Then
yes, Julia, I would like to ask you, I think it's related to that. So basically, when you have this vertical line at 10 to the minus 15 something, basically before that you only have the inflaton field, and other particles start appearing at that point. That's why you have this density of the particles that come up there, right?
Exactly. Yeah.
Okay. And then you can see that is pumping energy into these particles because the slope is not, for example, again, radiation at 8 to the minus 4, but it's 8 to the minus 1. So it's getting
Could you repeat the first part? The second part?
Say, let's take the blue continuous line, which is radiation. And normally, the radiation should go like 8 to the minus 4. But here it goes 8 to the minus 1 during the reheating, precisely because you are pumping energy into the radiation from the inflaton.
Exactly.
Okay.
Yeah, exactly. So exactly. It's exactly the point. And you see here, basically here, the inflaton density, I confused myself now with the red line, but here, I mean, you see the inflaton density is here high. So it's basically here the starting point. And then basically it starts to appear when it really starts to, so to say, oscillate and basically pumping in the energy exactly as you just said. Yes. Yeah. This is exactly the point now that we, so to say that here you get, so to say, this additional phase, which is, so to say, not the usual 8 to the minus 4, which is having a different scaling. And then, of course, if you now have in this phase the freeze-in production, it will be altered, as we will see in a bit. Because the Hubble parameter, as we saw, depends on the energy densities. So this will be changed. And as you also implied by the choice of wording with the dumping into the radiation, we will get some dilution effects. But this I show you step by step in the next slides. But this is exactly now why this is interesting to consider, because we change the usual scaling of the energy density of radiation. Yeah. Okay, other questions? Okay, otherwise I continue. Okay, so what are the takeaway messages here? First, obviously the Tmax here can be larger than the reheating temperature. And the reheating temperature and Tmax differs whether we have fermionic or bosonic reheating and depending on the reheating potential. Okay, so what I just said, now we basically have the freeze-in production now during the reheating time. And as I just already spoiled, there are two effects that will change the normal quotation mark freeze-in production if it would happen during the normal radiation domination. First are dilution effects. Where do they come from? As was already mentioned, at the inflaton, I basically pump entropy now into radiation. and this leads to the dilution of the rate, roughly. So I can write it down. So to say this is the entropy with respect to the entropy at reheating. And then it depends if I'm having bosonic or fermionic reheating, and on the potential if it's phi to the k equals 2 or 4. And you see already, if you plug in numbers, k equals 2, the dilution factor is the same. If you have k to the 4, you have a larger dilution for the bosonic reheating than the fermionic reheating. So this is one effect, we dilute the dark matter yield. The second effect I also mentioned already, as the Hubble parameter depends on the the evolution of the energy density that we have just seen are altered due to the reheating. I also have to include, of course, this is the second effect, so dilution and the altered expansion rate. If I then put everything together and try to create, in quotation mark, a master formula and compare with what I actually want to compare with, the Rayleigh abundance, I get this equation. So the first part looks more or less like the normal freeze-in. So we have the parent particle mass, we have the dark matter mass, we have the coupling of the parent particle to dark matter and the standard model particle. And we have here, I'm sorry, I was saying something wrong. This is the decay length. Sorry, the GS is of course the degrees of freedom. Mea culpa. I'm sorry, this was wrong. I meant the C tau. It depends on the coupling. And of course, we want to compare it later with collider results. This is why we have here the decay length. If I have the radiation freeze-in in the radiation domination, then I would only get here this part of the integral. So this here would not impact the Rayleigh abundance. But now, as we have this additional phase, so to say, between the end of inflation and this reheating phase, depending on the ratio of the reheating temperature and the parent particle mass. So how does it now affect the result? So you see, this is already looking very much what we are used to if we think about freeze-in. Here, the parent particle mass over the temperature. Here, the dark matter yield. Here, I'm frozen in to the right Rayleigh abundance value. A large reheating temperature, parent particle around 500 GeV, and a certain dark matter mass, roughly the value which is bound by Lyman alpha constraints. And you see here, the parent particle is smaller than the reheating temperature. So I recover the usual classical freeze-in during radiation domination. And of course, we have no impact. So this is why k equals 2 or 4 doesn't matter, because we are not sensitive to it. So now let's look what happens if I go into the regime when the reheating temperature is smaller than the parent particle mass. So you see now already that out of the previously described effects, you see a change for k equals 2. Remember, bosonic fermionic is the same. K equals 4, bosonic and fermionic is different. And you see now the reheating temperature is smaller than the parent particle mass. Of course, you see here there is an effect, but the effect is not yet huge. But of course, if I change or if I increase the hierarchy, the effect gets bigger. So we have seen this already before, where this comes from. The different cases impact the evolution differently. And generally, so here the dashed dotted line is here the bosonic case. So there's a tendency that the bosonic peaks later. Why? Remember, the dilution was stronger. And this we can, for instance, also see here. We have here now even a larger hierarchy. And here, for instance, we have the largest dilution for the bosonic case. Here, this is k equals 2 and k equals 4 fermionic. And we have here the largest dilution and therefore the largest peak, because if we dilute more, we have to produce more dark matter in order to get the right Rayleigh abundance. This is why the largest dilution leads to the largest peak in order to counterbalance the dilution, because in the end, the idea is to get the right Rayleigh abundance. So this is why the larger peak is more dilution. Okay, so we see already that depending on which scenario, the effect is different. But of course, if we go to the normal hierarchy, we don't see any effect. So, okay, now you can ask, okay, nice to have, but what is the impact actually when we want to interpret experimental data? Because this is in the end what we want to know. Are certain models allowed or not? And how do we interpret the results? And for this, what is interesting now, how does now the decay length, what we expect to get in principle to not overproduce dark matter, will change if we have, so to say, the parent particle which is larger than the reheating temperature. So this comes basically back here to this equation that I showed already before. Or, I mean, even you don't need to look in all the details. The bottom line is simply that depending if I have now bosonic or fermionic reheating and I want to not overproduce dark matter, I'm connected here via the coupling of the decay length. Or in other words, here I fix now the dark matter mass and the parent particle mass and only change the reheating temperature and ask myself the question, what is the corresponding decay length in order not to overproduce dark matter? You see, if we have a large reheating temperature, this is the normal case, we get for all of them the same decay length, and it's pretty large. However, if we go to smaller reheating temperatures, it leads to smaller decay length. And what you also see, the smaller, this was not by purpose, the smaller the reheating temperature goes, you see also a stronger effect in between the for instance, bosonic or fermionic reheating. So due to the larger dilution, for instance, you have here the smaller decay length because you need a larger coupling to produce the right amount of dark matter. So in principle, what one predicts, if one, so to say, is in such a scenario where the parent particle mass is larger than the reheating, or we produce the dark matter in the reheating phase, that we expect smaller decay lengths in generally, and depending on what of kind of inflationary potential, you expect even, so to say, a smaller decay length depending on what kind of scenario I am. So the smallest for the bosonic reheating, and here the larger one for the fermionic reheating. And this is, of course, what we have to keep in mind when we want to interpret our experimental data, or if we want to exclude certain models. And this is why I want to look now into collider constraints. So I don't want to go in all details through them, but just to give you a flavor what we did in our work, what we considered. Because now, of course, the interesting question is to what extent are these decay lengths already excluded, for instance, by long-lived particle searches at the LHC. And if we are in such a scenario with feebly interacting particle, as the name already says, we have feeble interactions, meaning long-lived particles, and we have different possibilities to produce long-lived particles. So it could be either that it's so long-lived that we simply go through the detector without any decay. This is the heavy stable charged particle search. Or it lives for a certain time and then decays in the detector. For instance, here, the displaced vertex searches, or also here the displaced lepton searches. And these are the ones that we took into account in order to compare how strong these constraints are. As I said, I don't want to go into all the details, just to give you an idea here. We took for the heavy stable charged particle, so the most long-lived, the smallest coupling. So to say here for the Majorana dark matter model that we studied, we took here the analysis from Calibi and Lopez-Honores et al. And for the scalar singlet model, we took an old study where I also was involved. And so to say, for the heavy stable charged particles, as I said, we get here long-lived particles. We get an ionization track, and in principle, two kind of searches exist, either the tracker only, if we only, so to say, go here to the tracker, or also the time of flight, if the decay is also outside the muon chamber even. And here, so to say, we can compare with a SUSY or gauge-mediated SUSY breaking model, and this is what we did. And then you get here, so to say, you have here the parent particle mass, we have here the decay length, and this is, so to say, here that the exclusion limits from the heavy stable charged particle searches that come from above. If we go to a smaller decay length, we have, for instance, displaced leptons. Again, for instance, the scalar singlet model, we looked here into the F decaying into a muon or an electron, and here we took searches from RPV violating SUSY. And then if you do this, as I mentioned already before, we have then exclusion limits for a smaller decay length. And if you then, so to say, go to the disappearing tracks, so here, for instance, we looked into a search which was also SUSY motivated, where we have degenerate lattice charginos and neutralinos. And so to say, what we have here, we have, for instance, a chargino decaying into a pi and a neutralino. And this we could also recast for our scalar singlet model, and took here two analyses that had different sweet spots from ATLAS and CMS. And then you see we get, so to say, here these exclusion limits. So bottom line, we took all these different searches into account, and then you can basically combine everything. And this is actually what I want to stress. And this is this plot here. So what you see here is the parent particle mass and the decay length for the leptophilic scalar singlet dark matter model. We fixed the dark matter mass. And now here are the three searches that I just mentioned we took into account: heavy stable charged particles, displaced disappearing track, and displaced lepton searches. And then here the lines, in order, basically, if you want to have the right radic abundance, depending on the different scenarios. So to walk you through, what we have here in red is, so to say, the comparing result, which is the normal freeze-in scenario and radiation domination. Then here in black for a reheating temperature of 100 GeV, and in blue for reheating temperature of 20 GeV. And then the different types of lines show you if it's basically K equals 2, 4, fermionic or bosonic. And in principle, what you saw already in the table before, we, so to say, move to smaller decay length. But what it also tells you that, for instance, this is now the same plot, but for larger dark matter mass. But you see already that, for instance, if you would have now thought you are having excluded parent particle masses up, whatever, to 300 GeV in this case, if we have another thermal history or another history in the evolution of the universe, this statement might be too strong, because it could be still valid for instance, lower reheating temperatures. And then you cannot simply say a reheating or a parent particle mass of 300 GeV in this model is excluded. And this is why I want to raise awareness. So one has always to specify, okay, one shouldn't be too quick with exclusions, but it depends, so to say, on the full thermal history of the universe that we have to take into account. And here, the similar plots for the muonophilic Majorana dark matter models, again, the same color code. And just to show you again that here you see that the exclusion limits, of course, here it depends on the reheating temperature and the inflaton or the reheating potential, what is basically excluded from the experimental limits, and we have to be careful in the interpretation. Okay, so far I only confronted now the freeze-in during the reheating epoch with the collider constraints. But in principle, what I took here still as a free parameter, the reheating temperature, if I have a certain inflationary model, is actually not random, but I actually can calculate it. So now my question was, okay, to what extent are these reheating temperatures reasonable, or for what kind of models, and so on. And this is basically what I would like to do in the last minutes, namely the constraints from inflation, by connecting them to the reheating temperature. So let's remind ourselves again what I said in the beginning. So this is the inflaton potential, and I said here, when we have the reheating phase, I get this generic potential. But of course, the relevant question is, okay, I put this generic model, or this generic potential, but where actually does it come from? So I want to show you now that this is actually not completely made up, but for instance, can be obtained for certain well-known inflationary models. So here, for instance, the E and T model, for the people who are more familiar with inflation might be well known. And you simply see what I want to stress in this slide is that if you start from these models, you basically, if you expand at the time of reheating, you basically end up exactly in this shape that I've shown you before, and it's kind of natural. But of course, if you now say you started from a certain inflationary model, you get clear dependencies on the inflationary model, because here this K, or for instance, here this K is directly related here to the potential, or here the coupling. And of course, what we also have to make sure is that if we want to connect to inflation, that we are in agreement with constraints that constrain inflationary models. So in order to check if this is all consistent, or to what extent even in the constraints on inflation can basically constrain our freeze-in scenarios, we have to look now into the constraints coming from inflation. So that the idea is now, okay, we see we can match this generic inflationary model at reheating with well-known models, also the Starobinsky model, for instance. But how can we constrain this now from inflationary constraints? So here's the sort of the experimental status from Planck. This is the so-called spectral index, which gives the so-called the NS. You see it's very narrowly constrained already. And here the so-called tensor to scalar ratio. And you see here from the Planck data, we are already very narrowed down. So this means if we want to have such a generic reheating potential that I included in the plots, the question is to what extent do we have constraints on the reheating temperature already? And we actually have this, and this is I want to give you as a spoiler and show you now. Okay, just to get a little bit a feeling of how we connected, you see here the spectral index, and we see here the tensor to scalar ratio. You see here for this so-called E and T model for different alphas, this was the free parameter. This one gives you the Starobinsky model. We are here we are here in the, so to say, in agreement with the Planck data. And for people who've seen this already, what we simply did is we can calculate, so to say, via the slow roll conditions. We can connect directly here to the experimental constraint. So this is the tensor to scalar ratio. This is here the spectral index and the scalar amplitude. We know experimentally what are the values. And then, so to say, what I can get are limits on the reheating temperature. Because what I can do, if I start from an inflationary model, I can get an expression for the reheating temperature. This depends here, for instance, on the number of E-folds or the Hubble parameter at the end of inflation. The Hubble parameter, for instance, depends here on the observables. And by doing this, I can connect constraints on the observables to constraints on the reheating temperatures. Or to show it in pictures or in plots, you see here the spectral index. You see here the reheating temperature for the different models. And now, depending of K equals 2, 3, 5, or 6, you see here that we get this here as the allowed region we have from Planck for the NS parameter. And you see we get here a lower limit on the reheating temperature in case of the K equals 2 scenario. So meaning the reheating temperature that I previously was varying as a free parameter has actually a lower limit if I really look into a specific inflationary model. And you see here, so to say, the spectral index, that's a lower limit on the reheating temperature. And you see, depending on the model, it can be quite different. So, okay, you can do this exercise now for all the different models, and then you basically get a lower limit on the reheating temperature. Okay, so now let's put these things together. On the one hand, the collider constraints, on the other hand, the reheating temperature, sorry, the inflationary constraints. And the cross-link is the reheating temperature that, so to say, we can constrain via the inflationary constraints. And this is the combination. So what do you see here? So on the one hand, these are now for the different inflationary models that you get an idea how much this depends on it. You see again the parent particle mass and the decay length. In gray are again the collider searches. And here the blue shaded regions are the exclusion limits coming from inflation constraints depending on the lowest or the dark matter mass. So here the lowest for the Lyman alpha constraint or then higher. What can one take away here? As I said already before, from inflation, we get a lower bound on the reheating temperature, a lower bound from the lower bound on the spectral index. So we get here a lower bound on the decay length. This is what you see here. This is the exclusion limit. And the relic abundance depends on the dark matter mass and the decay length. So the larger the dark matter mass, as we see here, the more stringent constraints, so we get more exclusion. This is also what you see in all of these plots. And what you in particular see in this case very nicely, we get here kind of a kink in the distribution. And this comes from the hierarchy of the reheating temperature with respect to the parent particle. So we have here, which goes with Planck to the -2, and then parent particle to the -2, and then parent particle to the -9. And so bottom line is here that besides the constraints from the collider, you can also take constraints from inflation and put things together. And you know already that if you have a certain inflationary model that gives you this reheating potential, you're actually not completely, you even have stronger constraints here for larger dark matter masses than the collider can give you at the moment. And the same you can do also for the scalar singlet model, but you see here the constraints are a little bit less stringent, for instance, in particular here in the middle.
Julia?
Yeah.
Sorry, I'm a little confused here. In the first plot, for instance, in the left, you have, whatever. In the left, in the plot in the left, for instance, what I am understanding is below the dotted line, for instance, all that region is excluded by the data of bicep combined with Planck, etc.
Exactly. Right? Yeah. Exactly.
But at the same time, I remember that before this analysis, you said that these contours represents they represent the correct those points that fulfill the correct relic abundance, or not?
It's simply now, I mean, okay, exactly. So in the previous plot, the reheating temperature was a free parameter. So here, as you see, I simply say, okay, I vary the reheating temperature, quotation mark randomly, and then say, okay, I don't want to overproduce dark matter. Exactly. So this is what I did in these plots. But now I say, if I have a certain underlying inflationary model, I get a lower bound on the reheating temperature due to the lower bound on the spectral index that I'm getting constrained from Planck. And then, so to say, I cannot choose randomly the reheating temperature anymore because I simply know that not all values are allowed anymore.
Yes. Okay. I think I get it.
So in principle, it's the combination of this plot. So you here see the spectral index, right? This is the value that is allowed. And you see here that if you, so to say, for lower reheating temperatures, the spectral index is too small.
Rule out, yes.
Exactly. And this is then what you see here in this plot, that in this plot, the even if I would not overproduce dark matter, I can only do it with a reheating temperature that is too small in order to be in agreement with the lower bound or the range of the spectral index that I get from Planck. So in other words, if I have an inflationary model, or depending on the inflationary model, I'm not free anymore on the reheating temperature, on the choice of the reheating temperature in order not to overproduce dark matter, as I'm constrained by the Planck data. Yeah. No, but what you said was exactly correct. So it's just once reheating was the reheating temperature was a free parameter and once not.
Thank you.
Yeah, you're welcome. And I mean, this brings me actually to the future prospects, because I think in particular with the CMB stage 4, this is interesting, and you might have seen it already, what I didn't say when I showed you the plot. So this here is the CMB stage 4. You see already with CMB stage 4, actually we have the potential to, I don't know, either you see something or to exclude the alpha equals 2 ENT model. So then you basically are left with the Starobinsky and the T model with alpha equals 1. And so to say, as here we see similar results, I pick here simply Starobinsky. And what you see here on the one hand in blue, the same limits I just showed you a slide before. And in pink, the future prospects for CMB stage 4. And you see here that we have really the potential to exclude even to higher parent particle masses than we, for instance, that we can do at collider constraints. And I think this is kind of interesting to really see this combination of collider searches and also the link from inflation in these kind of scenarios. Okay, I think I'm running late, so I don't want to hold you back from any other information here. I think I have said all. I wanted to tease you with one thing, so I just mentioned it, but you can ask me or we can discuss at a later point if you want, just contact me. But what I did not include, and this is why I want to stress is, of course, the decay happens in a thermal bath. And I was just saying this very naturally, but I was never basically mentioning that I included thermal corrections. And what I just want to raise attention to, but as promised, I don't want to go into details. What we also did in a very recent work, basically between Christmas and New Year, we put it on archive, where we wanted to see really if we do this in a proper calculation, not only semi-classical Boltzmann, to see how big can the effect of thermal corrections be. As a teaser, they can be large. So for instance, up to, depending on what you compare, 30 or 80%. So this, I hope, makes you enough curious to look into the paper. But I think it's also interesting to stress that, of course, if we talk about freeze-in, we also have to consider if thermal corrections or if our vacuum approach by not taking into the thermal masses or not taking interactions with the plasma are actually valid. And in our recent paper, we give some recommendations in which situations this is a good approximation or in which situations this is a bad approximation. But with this, I want to conclude. As you have seen, I think it's kind of interesting to see or to be really careful how we interpret experimental data. This is where I would like to raise awareness for. So in principle, what we have seen that freeze-in during reheating leads to smaller parent particle decay length in order not to overproduce dark matter. And we have seen also that in particular for larger parent particle masses, the limits from inflation are particularly strong with respect to the collider limits. We have also seen that the reheating potential, the nature of the coupling, can have an impact on the dark matter production and the interpretation of the collider limits. So for instance, baryonic versus fermionic reheating, such that really the long-lived dark matter particle or the long-lived surges really can shed light on the reheating dynamics. In case we see something, we can really try to narrow down what happened in the early universe. And you might ask, okay, why I'm interested in this, or why to bother for small reheating temperatures? In particular, we don't know, the lower limit is BBN. And if we would point to a lower reheating temperature, we could even maybe, or even baryogenesis, leptogenesis model would be excluded that basically are relying on sphalar interactions. Also, to be careful with thermal corrections, as I mentioned in the last bit, so there are many aspects that one should consider, but I think the most important bottom line for me is that I think it's very interesting to combine early universe physics with laboratory experiments and always try to look further if in the combination of different aspects we can actually learn more than by just looking singly in one or the other direction. And with this, I really want to thank you for your attention. And of course, I'm happy to answer more questions.
Thank you very much, Julia, for the very nice and very comprehensive talk. Question from the audience? Julia, in the model that you considered, what about the constraint from dark matter leader detection? All these constraints are not relevant for that case.
Exactly, because as we are here, of course, you're fully right. For instance, in a weakly interacting WIM freeze-out case, but as in this case, we are really having this feeble interactions. It's simply too small, so we are not sensitive to direct detection. For instance, limits in these cases. Yeah.
I see. Bastian?
Well, thank you very much for a nice presentation. And my question is about this. How do you call it? About this, the decay of the inflaton into bosonic or fermions. What? Maybe it's a very basic question, but what do you mean with that? Because in the standard model we have both kind of fields. So you are selecting one to couple the inflaton in principle just to gauge bosons, and in the other case just. But if that is the case, then how do you produce the other type of?
Okay, no, very good question. I mean, so where do I have it? Okay, so I mean, in principle, you're absolutely right. In principle, you want to produce all the particles. But for instance, we cannot, I mean, as the inflaton, for instance, here is a scalar particle, for instance. We cannot, for instance, we cannot produce directly, for instance, the standard model fermions. If you think about how to write such an interaction down. So in principle, what I mean here is what is the dominant contribution. And of course, if you have of course, this is very simplistic in this setup. And in principle, you want to produce baryons and fermions from the standard model. But what I define here as baryonic and fermionic is, so to say, the first step in a full cascade. Basically, does the inflaton mainly decay into bosons or mainly decay into fermions? Of course, then all the other standard model particles will be created. But for instance, in this model or in this setup, when we have here only the parent particle, which is here the boson, in this setup, we don't have any other fermion that actually can interact with the inflaton. Here, of course, you can still imagine you have here the inflaton decaying into the vector-like fermions. You could, of course, have additionally bosons. Of course, this would complicate the picture even more. But in this setup, these are basically the cases that you have. But I refer only to the first step.
Yeah, I was a little confused about the terminology, but now I understand what you were referring with this in this thing. But is there an argument to not a priori not to couple, for instance, the inflaton with the dark matter in the same way like with the mediator, like here?
No. The only thing is that we would have then I mean, in principle, you're absolutely right. In principle, I could write on such an interaction, right, that the inflaton directly interacts with the dark matter particle. But in this case, per definition, I would have not freeze-in scenario anymore, because if I produce the dark matter from the inflaton, it would directly thermalize with the bath, and I would directly be in a more freeze-out scenario. So to say, this is why we didn't look into it, because per definition, we would not have freeze-in anymore. But I think this is also some interesting point, because in my opinion, often when we think about freeze-in mechanisms, people mainly assume a certain setup. But I think, of course, it's a question, or in principle, if we make these assumptions, it has also some implications on an inflationary model that I can actually have. Because as you just pointed out, if I want to have a freeze-in scenario, per definition, I cannot have such a coupling. Of course, now one can argue, if I want to start with a model from scratch, how realistic, how natural, whatever it is, I fully agree with you. This is another story. And this is also why I said in an upcoming project, I really want to study this when we go from one or the other regime. Because, of course, one can say this is an ad hoc statement, but in our case, we simply wanted to see how can it be affected at all, and to what extent do we actually see changes.
Okay. And my last question is about the thermal effects. Considering the results that you have obtained in your work that you have presented, how much changes do you expect when you, in principle, when you include these thermal effects on the results that you have presented? Yeah.
No, it's a very good question. I have to say that I cannot give you the direct answer yet, because actually, okay, now I'm somehow lost with my slides. No, here. Because we just really finished this over the Christmas break, and I was asking exactly myself the same question, of course, because I mean, I cannot give you an numerical answer, but I can give you an intuition. And I think for this, I can show you this plot. So what you see here, in principle, very easy. This is the mass difference between the parent particle and dark matter in a logarithmic plot. So here the F is simply the P, what I've used before.
Yeah.
On the y-axis, this is the coupling strength of the parent particle with the standard model bath. So this depends on your model. The numbers here is now the approach that I did before. No thermal masses, just decay in vacuum with respect to our full calculation. And now you see that in principle, for small mass splitting, these effects can be huge. For large mass splittings, they are not that big. So the number that I would give you is something in the ballpark between 0 and maybe maximally 20%. As a very rough, you asked me in 30 seconds estimate. Because why? We have large mass splittings. Remember, the dark matter was 12 keV, the parent particle was in the GeV range. So we are here at the larger mass splitting. So this is why we are basically, in quotation marks, safe. With the coupling, this I cannot give you now by heart, because this combination, this G is a combination of different couplings. I don't want to say anything wrong now, but I think this is the range. Yeah.
Okay, perfect. Thank you very much.
Yeah, thank you for all the nice questions.
More questions from the audience? Julia, I had another last question. What about what would be the scenarios leptogenesis that you are thinking that are most likely to be ruled out by your analysis of inflation and the constraint that inflationary are imposing the reheating temperature. I suppose that is type 1 leptogenesis or rational leptogenesis. Which type of leptogenesis scenario do you think that is most likely to be ruled out?
Okay, no, very good question, but I want to be precise. I don't claim that I can rule out any leptogenesis scenario, right? I mean, so what I'm trying, okay, I can answer first the short answer and then the disclaimer. Not that here, I don't know, there are claims that I claim something which is too strong. So in principle, what I'm thinking about is simply high-scale leptogenesis or baryogenesis scenarios that rely on these Falaron interactions in order to translate for instance, the lepton asymmetry into the baryon sector. And for this, we need these Falaron interactions, and these Falaron interactions are basically switched off at around the electroweak scale, roughly. Meaning, if we would have a hint for a reheating temperature lower than the electroweak scale, these Falarons would not be active, and hence we could not rely on them when we, for instance, want to do high-scale leptogenesis, because they would not be able to translate a baryon into a lepton asymmetry. So in principle, what I'm thinking of is high-scale baryo or leptogenesis scenarios. However, this is what I want to stress in the end. I don't claim that I can rule out anything, because I only want to say this is the motivation behind looking also into lower reheating temperatures, because in principle, nothing tells us per se what the reheating temperature we have. Only if we have a measurement, but this is, I'm not claiming it's easy, because we would need to see a hint. For instance, we need to measure the dark matter mass to actually know where we are in the parameter space. We would need the decay length. Only if we have a hint, we could basically compare different models and say, okay, for instance, if this model would point us to a large reheating temperature, this would point that we can have these leptogenesis or baryogenesis scenarios. If we say, okay, this would point us more to a lower reheating temperature, one should simply also remind oneself that this would imply that certain baryogenesis or leptogenesis scenarios would not work anymore. But at this point, I don't want to claim that I can rule out yet anything on this basis. It's just as a motivation to have this in mind.
I see. Thank you, Julia. Thank you so much.
Thank you for the question. It's a very important question.
More questions from the audience? If there are no more questions, we thank Julia for the very nice and excellent talk. Thank you so much, Julia, for the very nice talk.
Thanks for the invitation.
You're welcome. And we meet at the next seminar.
Bye-bye.
Bye.
Bye.
Bye.